Hey folks, in this video we're going to be taking a look at some additional topics related to regression. Maybe not completely central to regression in terms of understanding the basics, but I felt like a lot of these topics really deserve their due. I should warn you right off the bat that some of these concepts have to do a bit more with multiple regression, which we're going to get to shortly, but don't let it intimidate you. These are all fairly fundamental concepts, and you'll see how they apply when we do get to multiple regression. Anyhow, without further ado, I want to introduce a new data set. Let's get to the top here. Again, I made up these numbers myself, but this is the idea here is that we have a data set about used cars. And our independent variable, our predictor variable, is the age of the car in years. So I think it's anything from 1 to 20 something. And how much the owner spent that year on repairs for that car. So, our hypothesis going into this would be, the older a car is, the more that the owner has to spend in repairs for the given year. Our regression output is as follows. One of the things I want to start off with is really just redefining, what the coefficients are when we're talking about regression. What do they mean? And so looking at the coefficient, this is a simple regression. We only have one predictive variable, so we're left with a y-intercept and a coefficient for age, which is our predictive variable. The coefficient, in simple linear regression, this is just the slope, says, and this would be true in multiple regression as well, for every single unit increase in the predictor variable, we would expect that the dependent variable, in this case repair bill, to be affected by this amount that is in the coefficient. So, if this is a positive number, we expect the dependent variable to go up. If it's a negative variable, if it's a negative coefficient, we expect the dependent variable to go down. And we expect it to go up or down by this amount for every single unit increase in the independent variable. Okay, just wanted to recap on that really quickly. So, it also allows us to make predictions, to say, okay, well, 3 years from now, say, how much more can I expect? So leaving aside the intercept here, let's just, make a prediction about a change and say, 3 years from now, how much more can I expect to be paying for my repair bill? This is going to take us, we would say, okay, 3 years from now, whatever my repair bill is currently, I would expect a single unit change would lead to an increase in repair bill of, we would predict about $91, $90.90. So 3 years from now, this is pretty obvious, we would expect the repair bill to go up by 3 times 90, leading to, what is that, $272.70. That would be the amount we would expect the repair bill to go up 3 years from now if I'm still driving around the same car. Now, let's go to the first concept I wanted to address in this video, which is defining a confidence interval around predicted changes. Right? So what if instead of asking, how much would you expect your repair, I think we were talking about, this is my car, right? How much would my repair bill go up 3 years from now? What would we predict? What if we actually said, well, let's actually get a 90% confidence interval around the amount that I would expect my repair bill to go up? Well, how do we do that? This is where we start using the standard error of our prediction. I defined this in a previous video, but what we would do is we would say, okay, we've got our prediction for an increase. That is 272.70. I'm going to rewrite this, 272.70. And our confidence interval is going to be defined as a plus or minus. That's our middle point, obviously. Plus or minus a t-value. This is the number we're going to have to figure out the number of standard deviations associated with 90% confidence. This is no different than everything we've done with sampling and all that. A t-value, and we have to figure out first of all our degrees of freedom. Now, degrees of freedom in regression. This is where we get a little bit into the realm of multiple regression. Degrees of freedom is defined by the number in your sample, and I had the number of data points you have. I had 60 data points. Oh, look, my drawing stayed. That's fine. We had 60 data points, -1 for the intercept, and -1 for every predictor variable that you are using. So in this case, we've got one intercept, one constant, and one predictor variable, age. So it's going to be 60 minus 2. So our degrees of freedom is 58. But if this was a multiple regression, in multiple regressions, just use more than one predictor variable. Let's say I threw in the number of miles driven. That'd be a very good predictor variable to add. And I don't know how much we paid for the car to begin with. So a more expensive car presumably has less repair bills. Well, I don't know that that's exactly true. But we'll use those as two additional predictor variables. Now what would our degrees of freedom be? Well, I'm using age, miles driven, and price of the car when it was bought new. And then I've also got the constant. So our degrees of freedom would be 56 in that case. So it's just n, meaning the number of data points you have, -1 minus however many predictor variables you have. That's your number of degrees of freedom. And why do we always use the t-table? Well, we always use the t-table because we're dealing with a sample here. Whenever we're doing regression is all it is doing something with your sample. So it's always you're never using population data. And that's going back to when we use the t-table. We use a t-table when we're not given the standard deviation of the population, and that's always the case when you're doing regression. You're never you're basically using your sample data to make predictions about the population. So that's why we always use the t-table when we're doing regression. So we say t of 58, and I said 90% confidence interval, so that would be an alpha of 0.1. We divide alpha by 2 because we're doing a confidence interval. There's two tails to this thing, so t of 58 degrees of freedom and 0.05 alpha. Okay, so let's first find 0.05. I always forget to do this. So there it is on the second to the left column. Go down to 58. Is that right? 1.672. All right, looks good. Let's go with that. So you've already seen this. I'm going to erase this and replace it with 1.672. And then we have to multiply that by the amount that the predictor variable has been affected by, the amount that we've changed the predictor variable. In this case, 3 years. That's what we were saying, right? A 3-year change in terms of age. How much is that going to affect the repair bill for the car? So we say times 3. And then we multiply that by the standard error of our coefficient for that predictor variable. So our standard error is 12.44. And that's going to give us, so we're doing a plus and minus, it's going to give us a confidence interval of between 210.28 and 335.13. So to put this into common sense terms, this means that 3 years from now we can be 90% confident that your repair bill for the year will be somewhere between $210 and $335 higher than it is now. All right, so let's go back to the topics to address today. So we've covered confidence intervals for predicted change, and we're going to talk about confidence intervals. We're going to talk about prediction intervals for the actual point of a prediction, and we're going to talk about confidence intervals for defining the actual mean of a population based on a certain point, but that's going to come in later videos. So right now we've just defined how to get the confidence intervals for predicted change. We've talked about degrees of freedom. And now I want to talk about something that we can't get using Excel. And that is the standardized coefficients, otherwise known as beta weights. These are the same things. Using standardized coefficients. So a lot of more sophisticated statistical software, like SPSS, will give you, when you do a regression, it'll give you the coefficients, like this, but it'll also give you something called a standardized coefficient. And what that is they've taken the the predictor variables, and they've translated them, they've standardized them, such that they all have a variance of 1. And what that means, by doing so, don't even worry about that so much. Really, the thing that is important is understanding what a standardized coefficient means. A standardized coefficient is the amount that the number of standard deviations that the dependent variable will change according to a single standard deviation increase to the predictor variable, to that predictor variable, right? Okay, so let me redefine that. If your predictor variable goes up by 1 standard deviation, the coefficient, the standardized coefficient tells you how many degrees of freedom you can expect your dependent variable to change. Let's look at what this might look like. Hopefully you can read this. This is an output from, it looks like SPSS. SPSS is, I think, the most widely used piece of statistical software, like not counting Excel, because Excel is not really statistical software. It does pretty well with statistics, but it's not only defined for that. SPSS gives you the unstandardized coefficient, which is what we're used to dealing with, and the standardized coefficients. And I want to point something out here. If you can look at the boxed area, this is also a car-related regression. I just pulled this off the internet because I don't have SPSS on this computer, unfortunately, so I can't show you. But actually, I think that would just confuse things. The important point is just understanding what you're looking at here. And so this is something to do with cars, vehicle sales, and notice something. On the unstandardized coefficients, this one independent variable here, vehicle type, it's 0.883, whereas price in thousands is only negative 0.046. So it kind of looks like it has less impact because it's a smaller coefficient in terms of absolute value. But when you get to standardized coefficients, it turns out the price of the car has more of an effect. You know, a single standard deviation in price has a much bigger effect, a negative effect, on the dependent variable, whatever that is, vehicle sales. Maybe this is just likelihood of, I don't know. But it has a bigger effect in terms of if one standard deviation change in the predictor variable has a bigger effect in terms of standard deviation change on the dependent variable for the price as opposed to the vehicle type. But you wouldn't necessarily have known that just looking at the unstandardized coefficients. So, this goes back to an example I believe we used in a previous video, which was talking about SAT scores and grades in terms of predicting high school grades or an SAT score in terms of predicting a student's college grades. And we said, grade point average, it might, in high school, there's only 4 points. There's not a whole lot of variance to that. So going from a B to an A might be a big predictor for college grades. But it might turn, and whereas with an SAT, it's now scaled out of 2,400 points. So, a single point change in SAT score probably not going to make a big difference in terms of somebody's college grades. But it might be that SAT scores are actually more important. But you wouldn't really know that looking at the just unstandardized coefficient. So a standardized coefficient helps you sort of understand their relative effects, in the broader scope. The disadvantage of just looking at standardized coefficients, also known as beta weights, you can see that defined here, is that it doesn't take into account the scale, and so it might be a little bit harder to read in that respect. So there's pluses and minuses to using standardized coefficients, but I want you to understand what they were and just to define it here. The last thing I want to talk about, I believe, so okay, we've talked about standardized coefficients, beta weights, what they are, is the F-statistic. The F-statistic actually is in Excel. It's pretty much going to be provided to you in every single piece of regression software. And what it is it basically says whether there is a significant predictive relationship in your entire regression equation. Now, in simple linear regression, that's pretty straightforward. It's basically, is there a strong relationship between my predictor and my dependent variable? In multiple regression, you're analyzing the whole regression, all the predictor variables you've thrown in there. Does it provide you with significant evidence, of a relationship, basically? So it doesn't tell you does any one specific variable work. It's sort of the whole thing. Does the whole thing work? And so the F-statistic, we're not going to get really far into this. The main thing I want you to understand is looking at the significance of the F-statistic. The significance of F is like the p-value for a coefficient. If it's low, that's good. And basically it says, for instance, if it is below 0.05, that means that it's the overall regression equation is significant at the 5%, the 95% level at least. Any lower than that, so if it's 0.01, that means the regression equation is statistically significant at 99%. And so that's how you interpret it. Really, what you care about here is the significance of f. F is sort of like the t-stat here, which leads itself to a p-value. So, thus, the F statistic leads itself to the significance of f. This is related to ANOVA, analysis of variance, which we're going to get to in a later video, but I wanted to bring it up here. You can just quickly eyeball this and see whether or not you've got, a good regression equation going. Thanks.